with regards to the calculus that we've been doing. Oh. Well, this is really going to slow me down. I don't have any markers at all. That's going to really slow me down. Let me. I don't see any under there. Oh my goodness. Down here? No, that would be awesome. Okay. Let me go steal some. All right, I just went to the 2 near classrooms and nobody has any, so I'll be right back. I'm so sorry, folks. All right, so what is U substitution? Would someone like to tackle that? Yes, Manette.
Integrate with something, chain function, you see that chain alongside.
Absolutely, and that's how we recognize when we can use U substitution in an integral, is by looking for an inside function and an outside function. Absolutely. U substitution generally, though, what does that mean? If someone were to say, hey, use U substitution, like let's say that I gave you the problem 2x minus 3 squared plus 8, 2x minus 3 plus 15, and I wanted to solve that. Yeah, exactly. You can substitute U for 2x minus 3, so what you're really looking for is an inside function that you can go ahead and swap plus 8U plus 15. And this suddenly becomes a much easier problem to do, where you can factor that, nice and fast, U plus 3, U plus 5. And then by the time you're done doing the zero product rule, and you say U is equal to -3 and U is equal to -5, now all of a sudden you're all done and you swap back to the original term. So then I'd say, well, 2x minus 3 is actually equal to -3. 2x minus 3 is actually equal to -5. And then from there you proceed the problem. So U substitution is this really fun way of temporarily swapping out a complex algebraic expression for a simple algebraic expression. And in the case of an integral, that's even more cool and more powerful, because when you say let U equal some expression, I'll keep the 2x minus 3, you also get to do the substitution of du, which is 2dx. And it gives you even more that you can swap out when you do your integral. So U substitution in an integral is like way cooler than just U substitution in algebra, because you get an additional substitution sentence. Not just one substitution sentence, you get a bonus second substitution sentence to swap things out and make the integral easier than it appears. Okay, so that's u substitution, and it comes from the anti-chain rule, like we said. So running the chain rule in reverse. Okay, so what about integration by parts? Come on, let me say one more thing about u substitution. Why are we even interested in u substitution? What kind of integrals are we trying to do? We're trying to do products. So u substitution allowed us a way to do a simple product where you had some sort of an outside with an inside, and then the derivative of the inside out here. But not every product comes in that form. So now we're looking at another type of product, which we call integration by parts. And integration by parts allows us to handle a situation in which you call the first part u, and you call the second part ub, and then away you go doing lots and lots of substitutions. So yeah, where does integration by parts come from? If u substitution came from the anti-chain rule, integration by parts came from the anti-product rule. We're doing the product rule in reverse. Exactly right. So we'll do the product rule in reverse. And like I said, right here, you know, when you do u substitution, you get a bonus substitution sentence. Well, with integration by parts, you start with a u and a dv, right? Like in our box that we're going to make here. So you start with 2 substitution sentences, and then you get a bonus 2 more. Right? So you end up with 4 substitutions that you're able to do. Very powerful. Going from 1 substitution to 2 substitutions, going from 2 substitutions to 4. So it allows us to greatly simplify an integral and turn a complex integral into something that's really quite simple. Okay, so given all of our various formulas for integrals, what are we ultimately doing? That's a pretty open-ended question. What were we going to say, Josh? Math. Yeah, we're trying to do math. Trying to calculate area. We're trying to be able to take any integral that we stumble upon, right? Although, to be fair, I've already told you that some integrals are simply not doable. So like e to the x squared dx, you actually just can't do that integral in that form. There's no finite integral. There's no finite antiderivative of that function, which is pretty surprising because it's such an easy function. I mean, it's just e to the x squared. So you'd think that there'd be an answer. I remember when I first took calculus and my teacher told me that you couldn't do that integral, I was like, whatever, I'm doing it today. And I sat down and I started trying to figure it out, and later I was like, oh, you can't do that. Yeah. So, all right. Well, that's where we're at. Let's go ahead and finish up our last integral here. Okay, so here we are, it's April 11th, and we're going to, what is it really? It's not April 11th. It is? Oh my gosh, it is. Just the other day earlier today I wrote down that it was April 13th. This sounds wrong. All right, so today's April 11th, I guess. And we'll finish 3.5, start 3.6. 3.6, we have 2 class periods to do, so we have plenty of time. And then I have a new joke for you today. Because I think I told you the one about a man walks into a lawyer's office and asked how much he charges. And the lawyer said $100 for 3 questions. And the guy said, that's a little steep, isn't it? He's like, yeah, what's your 3rd question? Okay, but this one I enjoy. It's a cute one. Why did the cowboy get a wiener dog? He wanted to get along, little doggy. Get along, little doggy. All right. So I think we did number 4. And we did number 5, and that leaves only this number 3 and the previous number 3. So let's do the actual number 3 there, which is just the integral of the natural log. This is a really fundamental integral that we should all be able to do. You know, it looks like it should be part of our simple list, right? And what's our simple list? We've got the integral of x to the n, we've got the integral of e to the x, we've got the integral of 1 over x, and we've got the integral of e to the nx. So this looks so simple that it should be something that's simple to do, and that we should definitely have the answer to. Now, I did give you the answer to this the other day, and you wrote it down on your formula sheet. And the answer turns out to be x natural log x minus x, which is not intuitive, it's not obvious, makes you wonder, like, why would that be? So we'll go ahead and try to do this integral, but the fact is, this integral is not something we know how to do. It's not one of our previous simple integral lists, and u substitution will not work. Let's just verify that. Will u substitution work? What would we let u be? What do we always let u be? the inside function, right? So if I let u equal z, then du is dz, and the only substitution we end up with is natural log of u du, and nothing happens. You know, we're stuck. So what else could we let be the inside function? I mean, I suppose you could say let u equal natural log z be the inside function. What would that be the inside of?
The entire interview.
Yeah, natural log z to the first, maybe? I mean, that'd be kind of weird. We could try to say, let's just make the whole thing be the inside function. And if that was the case, then du would be 1 over z, because the derivative of natural log is 1 over the argument, dz. So then the integral would become u. Oh, there's a dz on there. But then, unfortunately, we'd have to move that z over to the other side. No, that's what it would be. But there is no 1 over z in here to substitute out for the du. So that we wouldn't be able to do this substitution. Because we could swap out the natural log z for the u, and we could swap out the dz for du, but there's this other 1 over z term that's not present. So again, the u substitution fails us. Okay? Why do I show you that u substitution fails us? Yeah, I mean, we have to cover our bases, right? Like, we might as well try something simple, which is u substitution, before moving on to something more complicated, which is integration by parts. So u substitution failed us. So now we need to think, what would be what would be the integration by parts? So now what? Well, normally when we do integration by parts, like look at an example we did before, we did t squared natural log t dt. You would either write that like that and call that u and call that dv, or you could write it backwards and say natural log t squared dt, and then you'd call this u and that dv. Right? So if you want to use integration by parts, there needs to be a product. And then you need to arbitrarily decide which one goes first and which one goes second. So looking at this integral, do you see a product? Yeah, it's just the one thing. So make it be a product.
1 times that.
Yeah, 1 times it. That feels a little arbitrary and like trickery, like magic. But that's what we're going to do. We're going to say, let's go ahead and call this 1 times the natural log of z. Yeah, or natural log z times 1, right? Because we don't know which it could be. It could be natural log z times 1. But this is a pretty interesting and clever example of how mathematics can sometimes be so clever that you're like, who would have ever thought to just put a 1 there and call that part of the product? It seems so like cheap, you know, that you might not have thought of that, like putting a 1 there. All right, so which should we do? Should we call this u and this dv? Or should we call this u and this dv? Yeah. Now, the fact is, the honest answer is, we don't know. We don't know which one to do until you just try it, right? Until you try it, you have no idea if it's going to work or not. There's no like special intuition that you might have to say, oh, this is going to work. Okay, so which one do you want to try first? Okay, Josh is saying the bottom one. Is that okay with everyone? We'll try the bottom one first. Okay, so let's try it. So we're going to try the bottom one. And so the first thing we do is set up our box. And say, well, we're going to have our box here. And we do u, du, dv, and so I put in my u, which is natural log z, and I put in my dv, which is 1 dz. And so now who recalls what's supposed to happen here? First of all, what process are we doing on the left? And that process is the derivative. That should be obvious because we're going to process are we doing? The antiderivative, which again should be somewhat obvious because we're going from dv to v, so we're going backwards in derivative. Now who remembers what this side should be? It should get better. Or stay the same, but hopefully it gets better. Whereas over here on the right-hand side, what should happen? It should not get worse, or the same. And I think we saw that there's a little bit of subjectivity here in terms of what's worse and what's better, right? I would say, you know, coefficients, definitely, it's not worse. If a coefficient appears, that's not worse. And if a power function stays a power function, that's not terribly worse. So yeah, that's what we're kind of looking for. All right, So let's try it. Over here on the left, the derivative of natural log is just 1 over z dz. Because recall, we're always in this box, we're treating a variable as a function. So you always have to tack a dz or a dv or a du or a dx at the end. Whereas over here on the right, working our way backwards, we're just doing the anti-power rule of 1. So what's the anti-power rule of 1? That's really 1z to the 0, right? So the antiderivative would be add 1, divide by what you get. So it's just 1z, which is really just z. Yeah, 1z. So we have 1z, and that's it. So we've done our little box over here, just kind of looking on the derivative side. Natural log becoming 1 over z, I'd say that's better, because now it's just a variable instead of a natural logarithm. And on the right-hand side, 1 became z, which is not incredibly worse. I mean, I prefer a 1 over a variable, but it's not the worst. And in any case, this is going to be the real test. The real test is what happens when we use the formula. So recall the formula. The formula itself is the integration of the product rule, and it is the integral of u dv is equal to u, spread it out, times v, minus the integral of v. Now again, that's a formula, quote unquote. But what it really is a way of rewriting an expression in a different way, like translating it from Spanish to French. So it's just a way of rewriting it. We are literally saying that this integral is the exact same as this integral. And the hope is that whatever this thing is, which is hard and nasty and we can't do it, that when you get it over to here, this integral should be easy enough. Right? Easy enough to do with one of our former formulas. And so now this is really the proof of the pudding. Like even though I told you that up here on the box, the left-hand side should get better and the right-hand side should get not too terribly worse, the real test is whether or not this integral is now doable. Okay, so let's try it. We're going to substitute in what we had. So u, going back again to u, to make sure everything fits. Don't just copy that again. Let's make sure that all the parts that we have is correct. So if I put in natural log z, and then dv, which is 1 dz. And yes, so far so good, that was the original problem. That should equal u, which is natural log z, times v, which is just z, minus the integral of v, which is simply 1z, times du, which is 1 over z. And now that right there is the moment that we should all get really excited. Because what happens when you multiply z times 1 over z? Then they cancel out, right? So this is really where we know that integration by parts worked for us. The fact that we have, actually I'm going to rewrite that now as z, natural log z. Variables always go in front of a natural logarithm. So z natural log z minus the integral of simply 1. Because those z's canceled out. And the integral of 1, we just did it a second ago, the antiderivative of 1 is just z. So now we have z natural log z minus z plus z. There we have it. Integration by parts really worked in that problem, which is incredibly ironic and counterintuitive and unexpected because the original integral wasn't even a product. Even though we've been sitting here saying for days now that we're trying to take integrals of products. And by that clever trick of the mind, by calling something that's not a product with the number 1, we were able to use this method and get our answer. And there we have it. The integral of natural log is x natural log minus x, which Wolfram Alpha would probably factor out that x and call it x natural log x minus 1. So you can see it in either way. Hey there, Rosa. Now, from the very get-go, you don't have to write this down, but we said that you could have either written it as 1 times natural log or natural log times 1. And Josh, why were you inspired to say to the bottom one?
Well, because if you were 1, and you have to take the derivative of 1, you wouldn't go to 1.
Yeah, why not? What's the derivative of 1?
Nothing.
Yeah, 0. Everybody now, even though it worked out and we got it, let's try the other way. You don't have to write it down if you don't want to, but let's say that you had tried 1 times natural log of z. then you'd have called that u and that dv. And again, all you can do is just try it and see what happens. So then I would have had u, du, v, dv. And in this case, u would have just been 1, and the derivative of that would have been 0. Yikes. Although, I guess, yeah, no, it's just 1. I mean, there's nothing else to put there. Theoretically, this is all a variable of z. So theoretically, I should write down 0 dz. Because in theory, that's 1z to the 0. Okay, then over here, dv was natural log z. Now here's the real funny part. How do we go backwards? They're asking us to go backwards on the very thing that we don't know how to do. Right? So it's even more ironic. Like this right here is a colossal, catastrophic failure. Because not only did it result in 0, it resulted in the thing that we still don't know. So this wouldn't work out at all. I mean, I suppose what you could do here is just call it the integral of natural log z and like really cheat. But then what? Right? So you have the original integral u dv, and then become uv minus the integral of v du. So then u times v, u is 1z, times v, which is the very integral that we're still looking to find, minus the integral of v, which is the very integral we're trying to find, which is a double integral. But then dz is 0, so then that whole thing would go away. And we'd be left with saying that our integral is equal to z times the integral that we're looking for. And that's nonsense. How could the integral of what we're looking for be suddenly equal to the integral that we're looking for times a variable? Like that variable came out of nowhere. And then if you really wanted to be clever, you could divide both sides by that, because then it would cancel out on both sides. And this whole thing becomes a ludicrous 1 equals z. All right, so that really didn't work out at all, did it? So, yeah, so that's what happens when you choose the wrong way. And hopefully it's very obvious that that was a dead end, whereas the other way was a good one. Okay, wonderful. We have one more example to do with integration by parts, which is really fun, because it's going to be u substitution and integration by parts. You would theoretically do both.
So we have 2 u's.
What?
So we have 2 u's.
Well, you just do one at a time. But yeah, there would theoretically be 2 u's. It won't be as hard as all that, though. So take a look. What is this integral that we're trying to do? It's the last one. It's the integral of natural log of something. Now, we just said that we know what the natural log of u is. The natural log of u is simply u natural log u minus u, right? So right here, we have this complex algebraic expression, 5z plus 3. And what could we do to the 5z plus 3? We can just get rid of it. We can just substitute it, right? So right up front, we are allowed to use u substitution to simply make our life easy. So to do that, we would say let u equal 5z plus 3. Therefore, du would be 5z, which would be 1/5 du equals to z. And so right up front, what we do is a u substitution just to get rid of the 5z plus 3. So there's our u substitution, and now what we have instead is natural log u, and then the dz becomes 1/5 u. So how does everybody feel about that? That's our u substitution. The 5z plus 3 became a u, and then the dz became 1/5 u. And we just always put the 1/5 out front and the dz at the end. And in fact, at this point, we can pull out the 1/5, couldn't we? So we're just looking. So you'll notice the instruction said use integration by parts, but instead what we did was did u substitution to make it simple. And now we don't have to do this again, we just did it. We already know what the answer is. This is now part of our toolkit. And anytime you want to, you can now use this in your toolkit without having to redo the integration by parts all over again. So now at this point, I simply know that the integral of natural log would be 1/5 times u, natural log u, minus u. How's that? Is that fair? That we're now just saying that we know this answer and we can use it? Yep. And then we just plug back in what u was, which was 5z plus 3. So now we have 1/5 times 5z plus 3 natural log of 5z plus 3 minus 5z plus 3. And we're done. Looks pretty nasty. You know, I suppose we could think about trying to simplify that in a variety of ways, but I'm just leaving it. It's okay. Any of you are curious to know what Wolfram alpha would say about it? Now notice what variable are we using in this problem? But am I going to type that into Wolfram? No, I learned my lesson. Wolfram and Desmos only ever use the variable x, because otherwise you don't know what they're going to think you need. X plus 3, there we go. Hey, their answer is almost identical to what we wrote down.
They just left it as.
Yeah, well, they pulled out the 5x plus 3. So they used the formula, instead of using this formula, they used 1/5 u times natural log u minus 1, which I said was the alternative way of writing it. And so they have written down 1/5 5z plus 3 natural log 5z plus 3 minus 1. And that's how they have it. Okay, folks, just so you know, in case you've never seen Wolfram alpha before, it's not just a calculator. It's called computational intelligence. It's supposed to be able to answer any question you put to it. So if you ask some sort of really weird, crazy question, it should be able to answer it. In fact, let's just be funny here. How many chucks could a woodchuck chuck if a woodchuck could chuck wood? Do you guys know that phrase? How many chucks could a woodchuck chuck if a woodchuck could chuck wood? I wonder what they're going to say. I wonder if they're going to be funny about it. Oh, well, they're just telling you what it is. Okay, that wasn't nearly as exciting. I thought they were going to say something like 7. All right. Well, folks, we're done. You can all go home. No. By the way, remind me to give you your test back. At the end of last class, I left here and I was like, oh, dang it, I didn't give them the test. So I want to give them to you. So I put a little reminder here. All right. So, folks, did everyone pick up the next packet? Okay. We're kind of done learning rules, right? So we've got a lot in our toolkit now. We can take a lot of integrals. And in fact, we now know how to do all the integrals that we need to do for this class. There are certainly other integrals out there, like how to integrate a trig function like sine, or how to, well, I don't know, integrate other wild functions. But we've learned as many integration rules that we're going to learn. And now it's just a matter of applying them to do something interesting. So in this particular case, we're going to see how to calculate area, volume, and average value. So let me just go ahead and put all 3 of those up here on the board so you see them. The first thing that we'd like to do is calculate area, kind of a fun area. You know, previously we were just talking about how to find the area trapped between the function and the x-axis. Well, what if I had 2 functions and I wanted to find the area trapped between them? Okay, so that's what we can do now, is we can find the area trapped between any 2 functions, not just trapped between the function and the x-axis. Yeah?
What would I do this for?
Well, I mean, if that's what the boundary actually was between 2 areas, like, you know, land, like, you know, if you had a map essentially of the state of Arizona, for instance, you want to know how much area there was in different property boundaries, then you could do it this way, like you had a function that represented the property boundary. But I don't know. I mean, anything, I guess. Yeah. It is, exactly. It's just the difference between them. Yeah, what you would do, folks, and you can look at this, you would first calculate the total. Let's say you're going from here, so there's an A and here's B. You'd find all the area below the top curve, and then you'd find the area below the bottom curve, and you would just subtract it out. Right? Does that make sense? So you would just find all the area, subtract out the blue area, and that would leave you with the area above. And that's exactly right. It would just be the integral of the top function, which we'll call f of x, minus the area of the bottom function, which we'll call g of x. So, yep. That's all there is to it. You're just subtracting the top function minus the bottom function. It doesn't have to be two separate integrals. It can just be the integral of f of x minus g of x. And that's going to give you the area between those two curves. Okay, so that's the first question, is area. The next type of question we'll solve is how to find the volume of something. Now this is really interesting. Let's say that I wanted to find the volume of a cone. So like a birthday hat. You go to a birthday hat, you wear that whole thing on your head. Let's say you wanted to find the volume of a cone, like a geometric cone. First of all, the volume of a cone is not trivial. Is it 1/3 base times height? So you know a triangle is 1/2 base times height, but a cone is 1/3 base times height, where the base is actually a circle, so it'd be 1/3 pi r squared times the height, which is that way. So again, that's a non-trivial formula. I know that Archimedes knew it in ancient Greece around 200–300 BC. So they've known it for a while, even though they didn't necessarily have calculus the way we have it in Leibniz. So the way we would solve a problem like that, using the tools that we've been doing, is you take, say, a normal graph, and you take a normal line. So that's just a very basic line. F of x equals mx plus b. It's just a straight line. So there's your y-intercept, and there's your slope. And what you do is you take that line, and you allow it. You take that line, and then you allow it to rotate out around the board, into the board, and then out of the board. And it's rotating like a pig on the spit. Okay, so it's just rotating around and around. And so then that line drops down to here, and it's rotating out of the board, and then into the board, and then can you kind of see that we've created a three-dimensional object by allowing it to rotate around the x-axis? And using that method, we can then calculate the total volume of that shape. The fun thing is it doesn't have to be, strictly speaking, just a straight cone. It could be the volume of anything at all. So if I wanted to have this nice little like curvy shape right there, then I could go from A to B and take that shape and pop it out of the board, and we would create some sort of a, I don't know, like a vase maybe, or maybe like the cone that goes on a lamp, or who knows what, but it's just some wonky 3D object. So we can calculate the volume of anything that you can spin around the x-axis. So long as it's a symmetrical object with radial symmetry that can spin around the x-axis, we can calculate the volume of how big that thing is, including just a sphere. If I just had a half circle, and then I allow it to pop out of the board and spin around, that would create a sphere. And then we would know the volume of a sphere, which again is a formula they've known since antiquity, but this methodology would allow us to reproduce that formula. Okay, so that's another thing we'll be able to do is volume. The last thing is called average value. This is kind of fun. Let's say that you had a bank account, and so here's your money and here's your time. And the money in your bank is going like this. And what you'd like to know from A to B is what is the average value? What's the average amount of money you have in your bank? All right, so what would you say first of all? Like if this up here is $10 and this right here is $5, what's the average amount of money that you have in your bank? Maybe 7. Anyone's guess would be a good one, so long as you say number between 5 and 10. So what we're looking for then is a dotted line that would represent the average value. And what that means is that if I took the parts up here, the area that's sticking out on top, I should be able to melt that down and pour it into these grooves here, and that should contain all the area that you have. So if you consider all the area that's there, but then you kind of mash it all down, or if that's a substance like ice, you melt it and allow it all to sink down to an average level, then what's the average amount in that tank, or the average amount on the graph? Okay, so those are the 3 things that we're about to do as applications of integrals. Everybody super stoked? Applications of integrals, this is going to be awesome. Yes, it is. All right, so there right up at the top there, you can see above number 2. I don't know if I put it on your paper, I didn't. But you can go ahead and write it down. It's exactly what we just predicted, that the area between 2 curves, f of x and g of x, where f of x is above g of x, between 2 numbers a and b, is simply the integral of f of x minus g of x. So the integrand, what you're integrating, is just top minus bottom. Very simple way to memorize this. If you want to find the area between two curves, you do the integral of the top curve minus the bottom curve. Yeah.
So, what about if you have two the functions in the cross each other that small amount of two like that, but they're going straight up.
I don't know what you're trying to draw, Josh. Thank you. I was doing it wrong. Yeah, sure, we can find that area. The exact same way. We would just find that area by taking this curve and subtracting that curve. Yep, always just gonna be top minus bottom. It'd be kind of weird, like very interesting, Josh, if you did draw those symmetric, which they appear to be, and you found this area, this counterintuitively, the area could turn out to be 0. Because here, f of x is on top minus g of x, and so you're producing an area that's a positive value. But now it flipped, and now f of x is on bottom and g of x is on top, and therefore that would be producing a negative value. So you have a positive area over here, but a negative area over here, and you could end up with no area. Because remember, area above the x-axis is positive, area below the x-axis is negative. So now we're talking about which is on top, f or g. And if f is on top, it's positive area, and if f is on bottom, it's negative area. And f of x minus g of x. It's just whatever you say. Yeah. It's whatever. It's however you define it. That'd be pretty fun to do. We can certainly do it to see how that works out. Like, what would be a nice example? Yeah, I suppose a cubic would be the good way to do it, because if you did go ahead and do this cubic and then this cubic, right? So this area over here would be a positive, but this area over here would be a negative, because the function on top would have swapped. Yeah, we could easily do that. In fact, couldn't I just take a cubic that's mirror image of itself? I could. Yeah. We should be able to do that. Let's try it. These are fun and good questions. I know you're all chomping at the bit to do number 2. Let's just do number 2. Well, let's just say we have this cubic function, which is x minus 2, x, and x plus 2. So there's that. And then we're going to flip that around so that it's negative. Now we have that. And we'd like to find the integral. So you'll notice that over here, red is on top, blue on bottom, and then blue on top, red on bottom. So now if I do the integral, oh, gosh, I wish I could refer to those two functions. Take the 2. We're going to do this one. So I'm going to put parentheses on it. That one minus this one. There. Oh, my mouse clicked on the X. That is the most depressing. Wait, what?
Control Z.
You think that'll work in this context?
Control Z.
It didn't. Oh. I really wish it would have. Oh, it did! Josh, you're my hero. Okay. Dx. It seems to be telling me that I'm doing something wrong. What am I doing wrong? Doing the integral. Negative 2 to 2. Integrator must end with an integration variable like dx. I put it dx. Okay. Well, first of all, minus a negative, I might as well just put a plus there. You know what I bet? I bet it wants me to put a parenthesis around the whole thing so that it, there we go, and it came out to be 0. Yep, so it totally did. So even though there's area over here and area over there, the two are different signs, the area was 0. Okay, well that was a nice little experiment. Let's go ahead and start talking about Farmer Jones. And this is one of the weirdest problems ever. It says Farmer Jones and his wife, Dr. Jones, decided to build a fence in their field to keep their sheep safe. And since Dr. Jones is a mathematician, she suggests building the fences like that. So she wants to build these fences. And just a moment ago, Josh said, why would you ever want to do this? Well, apparently, Josh, there are people who want sheep fences that look like this. And it's very arbitrary, I admit. Okay, so anyway, that's their fence. Now, the first thing, folks, you'll notice that I gave you this graph. You're not going to get that on More. So I just printed that off with Desmos, and I put it on your sheet so we can all look at it together. But when you do these problems on your own, you'll have to go to Desmos, graph them, look at them, and actually determine which function's on top. So in this case, do you already know which function's on top? Wait, yes, the blue one. I mean, out of the two they gave us. Yeah, x squared plus 12 is up here. And then 4x squared is down there. Folks, how do you know that for sure? Yeah, the y-intercept, because if you plug in 0, it gives you the y value. So if I plug in 0 here, the y value is just 12, so it's way up here. If I plug in 0 here, the y value is 0, which is way down here. So there we go, that's our function. And we want to, now, here's a good question. Where is that actual point of intersection? Because I think we all think we know the answer. We all think we're integrating from -2 to 2. But honestly, can you tell that those two things really are meeting exactly at -2? You can't honestly tell. Because for all we know, it could be meeting at -1.999. That's true. We could just take a guess and say, what if I plug in 2? Will both of these have the same height? Because that's what we're really asking. A point of intersection means that the two functions have the same height. So if I plug in 2, they should both have the same height. So sure enough, here 2 squared is 4 plus 12 is 16. And here 2 squared is 4 and 4 is 16. So yes, they have the same height. So they really do intersect at the x value of 2 and the y value of 16. So we could go ahead and write that. 216 is that intersection point. Same thing over here. If I plug in -2, it would also still both give me at 16. So that's -216. Now, that was one way to verify what the point of intersection was. We took a lucky guess. But to actually confirm where we're starting at with A and ending at with B on our integration from A to B, you really do need to find the point of intersection. And the good news about finding the point of intersection, you find point of intersection by setting f of x equal to g of x. And so now that we've been in this course for a while, you should be able to tell me what that means. When I say f of x equal to g of x, what am I saying about the two functions? They're equal to each other, but what does the function represent about a function? It represents the height, right? So what are we really saying here in English? Exactly. So we're looking for a point on the graph where the two functions have the same height, which means it's a point of intersection. So really, we're using the idea of same height to mean it's a point of intersection. Okay, so then we just set them equal to each other. I'm going to do 4x squared equal to x squared plus 12, even though that's not really what we said. Well, I guess we didn't really find which one of them was after g. But I'm going to set them equal to each other, subtract the 1x squared, get 3x squared equals 12, divide up to 3, x squared equals 4. And so sure enough, x is plus or minus 2. And you might think, gee, we spend a little bit of extra energy finding out that the point of intersection was a 2, -2 is where it knew. But on other problems, you're not going to know where the point of intersection is. So you need this method to just know that you set the two functions equal to each other. And however many solutions you get is the number of times you have a point of intersection. Okay. Okay, so now, what integral do we do? The integral is always just going to be top minus bottom. So the top curve is, oh, and you know what? Everybody just try this just once to put some muscle memory in your hand. It's the integral of top minus bottom. That might feel silly to you to write that down because you're already like, okay, I already got it. It's top minus bottom. But if you write it down once, you have more muscle memory in your hand. It'll remind you to you later on. So we're going to do x squared plus 12 minus 4x squared x. And where are we integrating from? Yeah, -2 to 2. Now notice before we do this integral, we might as well combine like terms, we might as well, right? So that it's just a nice simple, instead of having lots of terms, so it's negative 3x squared plus 12 from negative 2 to 2. And now, while we're at it, notice that we just had a conceptual reframing. We were finding the area between those two curves, but now what are we doing? Yeah, exactly right. So we were finding that weird happy face shape, but now, by rewriting it like this, we're actually just finding all this area underneath that parabola. And we're saying that the area under that parabola, trapped between the function and the x-axis, is equal to the area trapped between those two smiley faces. So that's interesting to note, that we changed the problem from between two curves to a problem between the function and the oops, don't need that anymore. So add 1, divide by what you get, and that's really x to the 0, right? So add 1, divide by what you get, or go from negative 2 to 2. You'll notice that I'm always a little formal by keeping these fractions here, and I wait until the next step to simplify it. I know we could have probably all done that in our head, but negative x cubed plus 12x from negative 2 to 2. And now the fundamental theorem of calculus states you do parenthesis minus parenthesis. So I'm going to type in my structure, negative something cubed plus 12 something. Type in my same structure, negative something cubed plus 12 something. And then I type in my numbers, so top number and bottom number. Notice that that's also top minus bottom, isn't it? We're plugging in the top number and subtracting and plugging in the bottom number. And I think we could probably do all this in our head. So that's negative 8 plus 24 is positive 16. And then negative 8, so positive 8 minus 8 minus 24 is negative 16. So we really have 16 minus negative 16, which is a plus, so that's 32. Did anyone else get 32? Okay. And they didn't give us any units at all. So the area, that could be 32 square meters, it could be 32 square feet, 32 acres, 32 square miles, nobody knows. That's what, yeah, the last sheet. Okay. Well, folks, in the interest of time, we'll take our break right now. But you'll notice the next few problems are the same. They're going to give you two curves. I already graphed it on Desmos, so you can look at it, and you'll do top minus bottom. I would say the integral part is probably pretty easy, and the only thing we really need to do is just find the point of intersection. So now, do you all agree that this point of intersection is not obvious? Like, where's this point of intersection? Yeah, not obvious at all. I mean, maybe if you were on Desmos, you could just zoom in, or better yet, you could just click on it, and it would tell you. But even then, if you just click on it, it could give the decimal to you, and Desmos only rounds to 3 decimals. So if it gave you the decimal 0.414, you have no idea what that is. It could be. Yeah, so the key is looking alone is not enough. You need to actually find the point of intersection. So folks, let's just start a couple of these problems. And that way when we get back from break, we can move on to the next idea. So there's just 2 more of these. Let's just set them up so that we can all agree on what integral you're taking. And then you can do that yourself. So we're looking at the next problem. We're finding this area trapped between 5x and y equals 9x squared. Now, again, you'll notice I gave you the Desmos, so it's fairly obvious which function is on top. Which function is on top? The 5x, the linear one, and then 9x squared is on bottom, the quadratic one. But if you weren't looking at the graph, how would you know which was on top? How would you even know where they intersected? There'd be a lot left to think about if you weren't looking at the graph. You'd have to figure out which one's on top and which one's on bottom. But that's why we graph these things. Go to Desmos, use your graphing calculator. Okay, so let's find that point of intersection. Where is it? So you can set up 9x squared equals 5x. What is all that? Divide by 9 and then take the root.
No. divide by x.
Well, I'm glad that you said that. You're technically not allowed in algebra to divide by x right now. Who can tell me why? Because that might seem like really convenient, like, hey, also is next on both sides. We'll go like that and get 9x equals 5. But why are you not allowed to divide by a variable ever? What could x be? Well, yeah, it's the second, you just eliminated your second answer, because how many answers should there be to this problem? 2, and now we just reduced it down to a problem with only 1 answer, so we just lost an answer. But what could x be? But specifically, look at where it is.
0.
X could be 0. And can you divide by 0? You definitely cannot divide by 0. If you divided both of these sides by 0, you wouldn't get 9x equals 5, you'd get undefined. Because you divided by 0. But Josh, I like that you said it, because I'm sure a lot of us would be tempted to do that. There was a time where I did that, and I got like pages into a problem, and I got to this fantastic result, and then later on I realized, oh, that result's completely wrong, because I did something illegal. Okay, so what do we do instead then?
Subtract 5x.
Yeah, this is a quadratic, so we want to get all of our terms to the left. Right, folks? Anytime you have a quadratic, you always move all the terms to one side and set it equal to 0. Why do you set it equal to 0? Because the 0 product rule. So right now, if you wanted to, you can do the quadratic formula, A, B, and C. You'll notice that A is 9, B is -5, and C is 0. Or I think it would be easier just to factor, because now, Josh, you are allowed to factor out an x. That's completely illegal. Isn't that interesting? You can factor out an x, but you can't divide by x. And why is it that you're allowed to factor out the x? Yeah, it's still there. We didn't cancel it. Most importantly, we didn't divide it. And even now, x could be 0. And in fact, in a moment, we're going to say that we want x to be 0. And we're completely allowed to do so. So we have x equals 0, and then we have 9x equals 5, which is x equals 5/9, which is 0.5 repeating. So 1 point of intersection was at 0. We saw that on our graph. But even then, you can't assume that that was 0. You don't know. It could have intersected at 0.001. Right? We don't make any assumptions. And then this point of intersection is at 0.555 repeating, which is really 5/9. So where is our integral from?
0 to 5x.
Yeah, 0 to 5/9 of top minus bottom. So 5x minus 9x squared. And that's the integral that you all will do. We won't finish this one. You can finish it on your own. Notice the conceptual reframing now. Instead of saying finding the area between those two curves, which is this weird little slicey thing, what we're really saying is that it looks like that shape. That we're finding the area between that function and the x-axis. What does that look like? It's 5x minus 9x squared. So what we're really doing is finding the area between that area. And it already put it, it's correct, from 0 to 0.555. This is interesting to note, that we're finding exactly the area that's above the x-axis. Notice that that new shape that we're looking at exactly goes from 0 to 5/9. So when you conceptually reframe the problem from being the area between two curves, as opposed to this new function, which is simply a parabola that looks like this, it automatically adjusts itself so that the positive part is in between the two limits of integration that you want. It's very interesting. Okay, moving on. Last problem. So you're all going to go back and finish that, right? Because that's an integral. You can all do it. Now this problem, again, I gave you the graph so you can see what it looked like. Let's read it together first. It says, sketch the region enclosed by y equals e to the 2x, y equals e to the 5x, and x equals 1. So they just said to sketch that area. So if I were to have tried to sketch that by hand real quick, folks, what does e to the 2x look like? It's just an exponential curve, right? So asymptote over here to the left, and then it goes up. What does e to the 5x look like? Also exponential. Which one grows faster? Keep in mind that by exponent rules, when you have x to the a to the power of b, you can multiply x to the ab. Or if you had x to the 3x, you can separate it as x cubed to the x. Or, oops, I didn't want another x up there. That's a little awkward. Call that y. Or I can separate it as x to the y cubed. So it's totally my choice as to which way I separate those powers. So when you look at e squared to the x, I could call that e to the x squared. And I could call this one e to the x to the 5th. So which one grows faster? Which exponent, 2 or 5, grows faster? I mean, which is bigger, 3 squared or 3 to the 5th? Definitely 3 to the 5th. This one grows faster. Okay? Yeah. Maybe you're just feeling a little hesitant there. But definitely to the 5th grows faster. So when we're looking at a simple graph here, if we say that this is e to the 2x, e to the 5x would be up here. Right? So e to the 5x would be growing faster than e to the 2x. And so then what's this problem saying then? We have two exponential curves, and we want to sketch the region enclosed by them. So we're looking at this area in between them. Right? And x equals 1 is our right-hand boundary. So I'm going to go right here with 1, and I'm going to draw a line. So far, I'm only looking at this area. Well, how far does that area continue? Does it keep going over here with like this little sliver of space between them? Is that what they're saying? Between them going back to infinity?
Well, we're going to close up since they both go to the same paths.
Well, I mean, yeah, who knows? We know for sure that that's the right-hand boundary. Where's the left-hand boundary? Do they ever intersect? How do we find out if two functions intersect? We set them equal to each other, right? So this is our general strategy. If we ever want to know if two functions have the same height, we just set their functions equal to each other. So let's find out if these things ever intersect. So we would just set e to the 5x equals e to the 2x. Well, this is a bummer. What do we do? Now we could go at, well, yeah, what do we do? What do you all want to do? You could? Yeah, you actually are allowed to do that. Josh has a fine recommendation. You can take the log of both sides. Then the exponents on a log drop out in front. So you have 5x natural log e equals 2x natural log e. And what's the natural log of e? That's just 1. So now we have 5x equals 2x. So yeah, you can take the log of both sides. Now what? Can't divide that x.
I was going to say it's subtract, but
You can. You're allowed to. Yeah, x equals 0. So apparently, they don't just continue on like that forever. Apparently, they touch. Right there. And it does say, sketch the region enclosed by that, and x equals 1.
so we want this whole thing just skip that.
Just what?
So we don't have to solve, we just have to sketch that in.
No, we still need to solve for the area. Yeah, we still need the area, but apparently there was a natural stopping point there at 0. Now, by the way, we all know that they have the same y-intercept, because how do you find a y-intercept? You plug in 0. And so e to the 2x versus e to the 5x, what happens if I plug in 0? I mean, they both meet at 1. So they definitely have the same y-intercept. They definitely have a point of intersection. But we for sure know that. So now we can look at this and say, okay, we have a point of intersection here for sure. That's a 0. We have a point of intersection. Well, we don't have a point of intersection over here. We simply have a right-hand boundary at 1. So the area that we're finding is this area right there, right? So again, we kind of spent some time talking about all that because if you're just sitting at home and you get to this problem on more, they didn't give you a graph. So you would just have to take those curves and do what with them? Yeah, either draw them or go to Desmos and graph them or use a graphing calculator and graph them. And keep in mind, what's one challenge of plugging functions like this into a graphing calculator? The window will usually be terrible, right? Windows, normally when you just first plug something, the window is normally bad. It doesn't normally give you a good picture. So this, like, look, this is what Desmos just gave me, and they want to know the area but trapped to the right by x equals 1. Do I even have a good window for that? No, this is kind of weird. Like, I'm looking at this and I don't understand the problem at all. What do you mean trapped between green, red, and purple? I don't see any area trapped between green, red, and purple. So what do I have to do?
Fix it.
Yeah, I have to fix this. So now I have to change my window considerably. I need to go up really high, right? First of all, I'll cut out the left-hand side of the graph because I don't need to go to the left. I'll cut out the right-hand side of the graph because I only need to see to the far right if 1. And I don't need to go down very far, maybe just 10. And I'll go up quite a bit because I'd like to see the top of where, oh, there we go. Now suddenly I have a really nice graph. Isn't that just crazy how much that transformed itself from the first thing you saw? Right, so window adjustment should be the next subtitle of this class. What's the subtitle? Advanced techniques for algebraic simplification, manipulation, and window adjustment. Right, that's another skill that I hope you're taking away from all this. Okay, window adjustment. That's a very good skill. All right, so now we can actually do our integral, right? I think we can just write it down. So we're going from 0 to 1 of e to the 5x, because that's on top, minus e to the 2x, because that's on bottom, dx. I know I said I wouldn't do this with you, but we haven't done a lot of e to the integrals, and this one is just crying out to be done because it's so simple. What's the integral of e to the nx? It's just 1 over n, e to the nx. So look how nice and simple this integral would be. It would simply be 1/5 e to the 5x minus 1/2 e to the 2x integrated from 0 to 1. It's interesting, e, the function e, is such a trade-off. It's like, hey, I'm e. I'm infinitely wrong and I'm irrational and transcendental. Huh. But my derivatives and integrals are really easy. Like super easy. Okay, so then by the fundamental theorem of calculus, we plug in a 1, so that's just 1/5 e to the 5th minus 1/2 e to the 2nd by plugging in a 1, because 5 times 1 is just 5. And then plug in 0, but 5 times 0 is 0, e to the 0 is 1, so that's 1/5 minus that. So then we have 1/5 e to the 5th minus 1/2 e squared. What's 1/5 minus a half? Is it a nickel? Because 1/5 is 20 cents and 1/2 is 50. Oh no, 50 cents. 20 cents minus 50 cents is 30 cents. I'm just going to call that 0.3. Is that cheating? If I just look at a couple of fractions and I just think about pennies and dollars, and I'm just like, forget the fractions, it's 30 cents. Actually, it's not though. It's negative. So it's minus and negative 30 cents, so it's plus 1. Okay, well there's our answer. That's the amount of area trapped between those curves. Yep, you can just be done there. You could get a decimal approximation if you like. But that is the exact answer, and exact answers are always preferred by bosses and governments. But you can definitely get a decimal and approximate it with the decimals. Okay, now let's take a break. So it's 12:06, let's be back at 12:16. It'd be super fun to actually create a math class called Advanced Techniques for Simplification and Algebraic Manipulation and Window Adjustment. And then once you get to class, I'm like, all right, we might as well learn calculus. And we still learn the exact same thing. It just changed the name of the course. It'd be kind of fun. Mistakes. You what? Mistakes. What mistakes?
Oh, I tried to do a problem.
What problem?
This one.
No, I didn't.
Dropped off the fractions.
Oh, you did?
So I think it's good sometimes.
Hey, I mean, probably, I'm pretty sure they've done studies on this, but we learn most from mistakes. Yeah. Oh, for sure. They've done studies. when we do something correctly, we don't learn anything. Obviously, we didn't learn anything because we already knew what we were doing. We got it right. So you literally didn't learn nothing if you do something the right way, other than maybe reestablish or reiterate the patterning of your behavior. You didn't learn anything. But when you make a mistake, that goes well. Well, I certainly do feel good at getting things right. I'm with you there. Yeah, my wife teases me all the time because I tell her how good I feel when I get 100% on something. And she says, really, Jimmy, that's what you need in life to feel good about yourself? Not that you're married and you have kids and you have a good career. It's getting 100% on a test. And I'm like, basically. Yeah. Sometimes I need a win, and that's a win. So I watch YouTube channel called Legal. Yes.
It's this guy who evaluates the legality of stuff.
Oh, that's interesting.
Many.
Oh, okay. Not the legality of the movie itself, but the legality of what they do in the movie.
Yeah. Like if it's accurate.
Yeah.
So your wife's like, yeah.
Oh, yeah, that's super fun. Oh, I'm sure we both like that. We definitely look at things, I mean, I'm sure everybody does when you're watching a movie and you're like, that's not at all realistic. Yeah. So it's called Legal Eagle? Yeah. Well, that's fun. I'll text her right now. See if she's heard of it.
You know, somebody was like, to start watching video, maybe watching repetition live.
Wait, what?
I say it's recording right now and you're teaching, and I open up the video on my phone, I can be watching it.
Can you really? Try?
I've tried it, yeah.
Does it work?
Yeah.
Nuh-uh.
Yeah.
You're hilarious. That's fun, Sarah. I didn't know you could do that. Thanks for letting me know. I wonder how I turn that feature off. What if I'm like, no, I don't want people to watch me live.
Are you filming like right on YouTube?
Hmm?
Yeah, that's part of your life.
Wow.
Yeah.
Interesting. Alrighty, everybody's back. Colleen, what'd you bring us? Oh, it's very good. We should integrate the caramel latte. All right, so we finished with finding area between two curves, and so now we get to start looking at volume. I would like to make sure that visually, the idea of finding a volume of revolution is something that visually is intuitive to you. So let's just take a pop over to YouTube and do volume of integration visualization. Ah, this is a good one. We don't need to hear it, but you can all see it, right? So that's just the function y equals square root of x. And then they're going to also draw a straight line. And they're going to take that and pop it out of the screen and rotate it around and around. Okay, after they ended. So they're going between 0 and 4. There's the area that we would have found, and we will find that area, but it then rotates around and around and creates a 3D volume. So that's called a volume of revolution. And you do it by taking one slice. How thin of a slice? Infinitely thin. And how many slices? Infinitely many of them. And since you're looking at an infinitely thin slice, all you're really having to calculate is the area of that slice. So if you can calculate the area of the slice, then the thickness is infinitely thin, which we call dx. And then we can add all those together and find the volume of that particular shape. So now let's go back here. So this is the problem they gave us. And you'll notice up there, we might as well all write this formula down right now. It says the volume of the solid obtained by rotating about the x-axis, the area bounded by the curve, the x-axis between A and B, is that integral. So whereas moments ago, we had an area formula that looked like this, top minus bottom. Now we have a volume, so that was area. Now this is volume. Our volume formula is from A to B of pi f of x squared. Now that formula should be evocative, not provocative. Evocative. What does it evoke from it? Pi f of x squared. What does that look like? Circles. Yeah, circles. Because what formula do you know about circles? Well, pi r squared. So everybody know that the formula for the area of a circle is pi r squared. And so the idea is that when we take this line right here, and then we map it down, and we create this three-dimensional object here, and then you take one slice, and you take that slice, and you take it out and you look at it, what is it? So it's always going to be a circle. And you want to find the area of that circle. And the area of a circle is pi r squared. But in this case, what is the radius? Yeah, the height. So the radius literally is the height itself of the function. So what we're really doing here, like if you just wanted to write something down to help memorize how to find volume, it's pi r squared. You're literally finding the volume of a whole bunch of circles stacked together. Infinitely thin circles that are all stacked together. So it's really pi r squared. And we think, well, what's the radius again? The radius is not from the x-axis to there, which is the radius. And so your formula is pi f of x squared. So that's it. Right at this point, we just do the integral, and that tells you the volume. Well, let's go ahead and walk our way through one problem in which we kind of look at all this, okay? So let me go back up to the top here. So number one, you want to find the volume of the solid obtained by rotating the curve about the x-axis, the region under the curve, y equals x to the 1/7 between 0 and 4. So again, you'll notice this graph. I got it from Desmos, and I pasted it onto your paper. So first of all, what is x to the 1/7? Is what?
It's an exponential of different.
Okay. Yeah, you got it there. What? You all know what x to the 1/2 is. Is the square root of x. So what's x to the 1/7? Yeah, so we're really just looking at the 7th root of x. And yes, just like a square root function is a parabola turned sideways, x to the 1/7 is a 1/7 graph turned sideways. I'm sorry, it's an x to the 7th graph. So it is the polynomial x to the 7th turned sideways. Okay. So we're looking at this graph, which is really just the 7th root of x. And it says you first slice through the rotated solid at a generic point x and get a circular cross section. What is the area of the circular cross section? So everybody go ahead and just draw your own little mirror image down below it. Mine's not perfect, but the idea is that you're flopping it down, a mirror image down here. And then we're going to choose an arbitrary point x. We're going to go straight up, straight down, and we're going to do our best 3D drawing to make it look like a little cross section coming out of the board and going into the board. And what we'd be looking at, if your drawing is better than mine, if you take it out and look at it, is a circle. So we now have that circular cross section, and the radius is equal to f of x. x, because it's telling you the height at that generic point x. And so they're saying, what is the area of that circular cross section? Well, the area of a circle is pi r squared. And in this case, r is just f, so it's pi f of x squared. So that's our area so far. We can report that right here at a of x. Now probably, if you just write pi f of x and the squared on the parenthesis might be enough. But that could be ambiguous to someone, like, hey, are you squaring the x or are you squaring f? And so maybe an extra set of parentheses doesn't hurt. After all, if it was pi r squared and you wrote r empty, it would be pi something squared, and that'd be writing the function empty like we do. And then putting f of x in it, that's what it would look like. I'm just like being like a real English teacher here, talking about capitalizing your sentences and using the Oxford comma correctly, right? So 2 sets of parentheses I think works best. Okay, now this makes the volume of the approximating disk with thickness delta x. So they're saying the thickness is delta x. You could just as well call it dx, equal to what expression? So what's the volume of the disk? First of all, does anyone remember the formula for the volume of a cylinder? Maybe you can draw a cylinder. Well, that was going to be the cone. There's no 2/3 here. Did you say 2/3? No 2/3 here. But it's going to be, for any prism, the volume of any prism is the base area times the height, or how tall it is. So what we have here, a base area is just a circle. So that's the circle. And then the height is however thick it is. So in this, if we're thinking about it in general, that's the height of the cylinder. And then B refers to the base area. So in that case, the base would be a circle, pi r squared. So what we're saying then is that the h is really delta x, and that the base circle is pi f of x squared. So then the volume of the disk, if you think about the volume of a cylinder being base times height, would be pi f of x squared dx. And you'll notice that we just recreated the formula. That's the formula that they gave us right up front. So in actuality, what is this formula? It's the formula of a cylinder, which is really funny, because is this thing a perfect cylinder? No, it's a curvy cylinder. And yet, by using the formula for the volume of a cylinder, where we're saying each slice is an infinitely thin cylinder, then by stacking them all together and adding them using the integration symbol, we are in fact finding the volume of infinitely many, infinitely thin cylinders. So we are claiming that each individual slice is a cylinder. Even though the whole thing is curvy, each individual slice is a perfect cylinder. Okay, so now let delta x approach 0, the sum of the volumes of the implemented disk that approximate the solid revolution. What total volume do you get? So we would jot down the integral 0,4 of pi f of x squared dx. And from here we start, actually putting in the function and manipulating. So what couple of things can we do? What can we do with the pi? And we can bring it out. This pi is just a number, 3.14, bring it out. And then instead of f of x, we write, x to the 1/7. So far we have pi, integral from 0 to 4, of x to the 1/7 squared. And how do we rewrite x to the 1/7 squared? X to the 2/7. So now we have pi, 0 to 4, x to the 2/7 dx. And look, that's a remarkably simple integral. We have a formula for that. That's just a power function. So we're just going to do the anti-power rule to integrate x to the 2/7. So what does the anti-power rule say? We add 1 and divide by what we get. So adding 1 is really adding 7/7, right? So that's going to be x to the 9/7 divide by what you get. There was a pi out front. And integrating from 0 to 4. And what is 1 divided by 9/7? Yeah, 7/9. Hopefully you all have or are developing a visual intuition that 1 divided by the fraction is just the reciprocal. So 1 divided by 9/7 is just 7/9. And then there's a pi times 7/9. What's pi times 7/9? You could just write 7 pi 9 if you wanted to. Or you can leave it separate, it's up to you. So what we have now is 7/9 pi x to the 9/7 evaluated from 0 to 4. Now, I don't know if you're looking at my work saying, gosh, you're rewriting this thing a whole bunch of times. But, what's that, Rosa? Oh. I mean, I think that's kind of the point of mathematics, is that you're supposed to rewrite something a whole bunch of times to clearly demonstrate the one leap in logic that you're taking every time. If you do too much at once, it becomes no longer clear to your audience or your brain what you're doing. So we're just doing one little thing, we're plodding along. So now, finally, we know that we have to do the fundamental theorem of calculus. But what can we do with the 7/9 pi? Can we keep that outside of the fundamental theorem of calculus? So can we write down 7/9 pi, big bracket, and from the big bracket, can we do our parenthesis minus parenthesis? Yeah, because that way we're not carrying along the 7/9 pi with the whole thing. So we can just have 7/9 pi, and then it's going to be something to the 9/7 minus something to the 9/7, and it's just going to be 4 and 0. I don't know if we know what 0 to the 9/7 is right off the top of our head. I mean, our assumption is that it's 0. Is it really 0? I mean, 0 squared is 0, 0 cubed is 0, square root of 0 is 0, cube root of 0 is 0. So can we just go ahead and make the assumption that 0 to the 9/7 is 0? What should we do to check? Maybe type it in your calculator, you're really sure? It is 0. So 7/9 pi and then 4 to the 9/7. I honestly don't know if there's a nice, concise way to write this. 7/9 pi, 4 to the 9/7. How ridiculous. What number is that? Now, for sure, we probably want a decimal. Because we want to wrap our mind around how much volume is it? Is it 3 cubic feet, 3.2 cubic feet? How much volume are we talking about? That was 0. Now, how do you type that into your calculator? Answer carefully. But it's going to be parenthesis 7 divided by 9, parenthesis, parenthesis pi, parenthesis 4 caret, parenthesis 9 divided by 7, parenthesis, parenthesis. Nice, everybody practice typing that in your calculator. Did anyone else get 14.5? Point 5, 2, 3, 9. Really 5, 2, 3, 8, but it ends up 9. Okay, and they didn't tell us what unit they were talking about, so it could be cubic inches, cubic centimeters, cubic, who knows? Cubic miles. It could be the volume of the earth being scooped out by the aliens. Yeah, that is approximate. Yeah, good point. That's approximate. All right, well, we just did it. Now, maybe looking at all that, that seemed a lot. All we really need to know is the formula. Pi f of x squared. All right. So this next one, they're asking us to determine the volume of the solid by generating this function around the x-axis. What would you get if you rotated that? A sphere. Yeah, you get a sphere. Well, it would be a circle that you'd look at first, but then popping it out three-dimensionally, you would have a sphere. So does anyone know the volume of a sphere? Really close. Oh, is that what we said 2/3 earlier, maybe? 4/3 pi r cubed is the volume of a sphere. You mean originally, like Archimedes back in the day? I don't know his exact principle. Yeah, they didn't have calculus. They didn't do it this way. The cone would be 1/3 pi r squared height, whatever that.
So then what is the 2/3 thing?
2/3 would be if you just wanted the volume of a semisphere, like just the top. Like if you cut that, if you divide that by 2, you get 2/3 parameter. I don't know a 2/3 formula. Okay, well, so that's the formula for the volume of a sphere in general. And if we just look now at this circle, what's the radius of this circle? Yeah, 4, we think, right? There's no 4 right there. But could we figure this out real quick just to be sure that it really is 4? How would we know? If you plug in, oh yeah, good point. If you plug in 0, then you would have that number right there. And if we do plug in 0, we have the square root of 16, which is 4. So this is a circle of radius 4, a sphere of radius 4, and therefore we know ahead of time what the volume is. It's 4/3 pi 4 cubed, which is 4, 16, 64, 256. So it should be 256 pi. So we know ahead of time what the answer should be. And now we just get to go do it and see if that's what we get. So our formula, which you have written down somewhere, pi r squared, really pi f of x squared. So we'll do our integral from -4 to 4. How did I know from -4 to 4?
Well, because it's the
Yeah, that's the radius. So -4 to 4 of pi f of x, which is root 16 minus x squared squared. Now this is kind of fun because what happens when you square a square root? Yeah, they just cancel out. That's really nice and tidy, isn't it? So I'm going to bring the pi outside. So pi, -4 to 4 of 16 minus x squared dx. That's a remarkably simple integral to do, isn't it? So I'm going to call that 16x to the 0 just to help my brain do the anti-power rule. So add 1 divided by what I get. Add 1 divided by what I get. From -4 to 4. And I've got my pi outside of the whole thing. So I have pi times a big bracket of a parenthesis minus a parenthesis of 16 something minus 1/3 something cubed. 16 something minus 1/3 something cubed. Where we'll plug in 4 and -4. It's so satisfying to write that down, and then you're like, oh, I have to now type that in my calculator. Should we type that into our calculator? I mean, yeah, I think we probably should. Because it'll give us some sort of a clean answer, right? So 16 times 4 minus 3 -4 cubed. Make sure you're doing that -4 cubed properly, where you need the -4 inside parentheses before you cube it. So there's a -4 times -4 times -4. Yeah, Josh? Oops, not -4. Oh, did you see what I did so terribly wrong?
Yeah, that's what.
That's terribly wrong, wasn't it? Should have been 4, 4, -4, -4. Good catch, folks. So now my calculator gave me, for my first number, it gave me 42.66666. I can write that down if I like, but at some point I'll probably hit math frac and get the actual fraction answer. And then I got a -42.6. Which is a double negative, so that's really plus. So we're going to add 42.6 plus 42.66666. And so that gives us 85.3 repeating pi. So 85.3 repeating, is that the same answer we started with? And maybe, so you take your 85.33333, hit math frac. Oh, it failed me. It didn't frac my frac. So what do I have to do that it didn't frac my frac?
Back to 6 by 3.
Well, yeah, I can always just go over there and check that. But no, what you have to do is put more threes. So apparently my calculator didn't have enough threes, so I have to hit more threes. You have to fill up at least a line of threes. And then it will frac your frac, and it gives me 256 thirds. So it only does math frac if you have enough decimals. Because like if I just typed in 85.3 and I told it math frac, it would think it's really just 85.3. And it would give a very different answer. That would be 853 tenths. Whereas if I put in 2 threes, it just leaves it as 80. Oh no, math frac. Look at how interesting. So if I do 2 threes, it tells me it's 8533 over 100. Then if I do 85.333, so now 3 threes, and I hit math frac. See, this is interesting to see how your calculator thinks. It's going to do 85.333 over 1,000. Now you obviously see the pattern, right? So at some point, though, the calculator is going to be like, oh, that's a whole lot of threes. And it's going to change its mind, and it's going to say, hold on, I think that's infinitely many threes. And then it's going to say that's 256 thirds. Isn't that fascinating? What's the changeover point when your calculator is like, hold on. Is that infinitely many threes? Because I think you mean infinitely many threes. And then it does a different calculation. It's kind of fun. Okay, so we did it. Now, folks, bonus question. What if we didn't know the radius? Let's call that radius r. How would this problem turn out differently? Yeah, we're going to go from negative r to r. And therefore, what's our function? It wouldn't be 16. They got the number 16 because it was 4 squared. So what would our function be? Be the square root of r squared minus x squared. Now, just in case it's been a while, or maybe you've never seen this, but the formula for a circle is x squared plus y squared equals the radius squared. That's the formula for a circle. And so if I wanted to solve for y, I'd move the x squared over and get y squared equals r squared minus x squared. And then I square root both sides, and I get y equals the square root of r squared minus x squared. Okay, so that's the formula we have. What would that integral be? This is a bonus question for us, a really good question. What if we wanted to take the integral of pi f of x, which is root r squared minus x squared dx, from negative r to r? What are we calculating here? The volume of a sphere of radius r. So this is the general problem, right? What formula should I get? Sorry, I'm in the way for some of you.
4/3.
I should get 4/3 pi r cubed. So will we get it? So oh, that's squared. So it'd be pi from negative r to r squared x to the 0 minus 1x squared dx. And then anti-power rule, so x to the 1, r squared over 1 minus x to the third, 1/3 from negative r to r. So then there's still a pi outside, we just won't forget that there's pi. So that's r squared x minus 1/3 x cubed from negative r to r. And now we plug it all in, right? So that'd be r squared something minus 1/3 something cubed. And here we're plugging in r, and here we're plugging in negative r. So just looking at this, does it seem reasonable that we might end up with something that's r cubed? Because r squared times r is r cubed, that's already r cubed. We got a whole bunch of r cubes here. So it's looking promising. So that's going to be r cubed minus 1/3 r cubed. And then that's minus a negative r times r squared is negative, so minus a negative is plus r cubed. And then minus a negative, but that's also negative. So it's still minus 1/3 r cubed. Now what do we have? R cubed plus r cubed minus 1/3 minus 1/3. So that's 2r cubes minus 2/3 r cubes. So what's 2r cubes? I suppose I can just take that. Minus 2/3 r cubes. How can I rewrite 2 as a fraction of a 3? Then 6/3 r cubes minus 2/3 r cubes, which is?
4.
And we had a, so the formula for the volume of the sphere is 4/3 pi r cubes. Isn't that nice? That's neat. I mean, this is a really impressive result. That we just used calculus to reproduce the formula that somebody found out over 2,000 years ago without calculus, right? That's pretty amazing. All right. Well, we've done a couple volume problems now. So here's one more volume problem, I think. Well, actually, there's a couple more volume problems. And I want to have time to do an average problem. So let's just set these problems up and you can finish them. That would be a fun problem for you to do on your own, by the way, if you want to go home and reproduce the formula for the volume of a sphere. You know now how to do it. All right. So what did this problem say? Find the volume of the solid obtained by rotating the region bounded by 2x squared, x equals 3, x equals 4, and y equals 0. That's a mouthful of different things. What are all those things? Let's draw it together. Draw a graph. Where are all those things? So the region bounded by 2x squared. What does 2x squared look like? Yeah, well, let's draw it on our own. What does 2x squared look like? A graph. And then we're going to be bounded by x equals 3. Now remember, x equals 3, they're not telling you the value on the x-axis. They're telling you the equation of a line. The equation of a vertical line is x equals the x-intercept. So this is the equation of a vertical line. This is the equation of a vertical line. And where do those vertical lines go through? Yeah, 1, 2, 3, and 4. So that's a vertical line, that's a vertical line. Okay. Actually, no, what we'll do is we'll just end class today talking about volume, and we can do the other stuff next time. We have 2 class periods for this section anyway. Okay, so far we're trapped between 2x squared on the top. We've got 2x squared on the top. We've got 3 on the left, 4 on the right. And what's trapping us on the other side? Equals 0. That's not a point on the y-axis. That's the equation of a horizontal line. So this is a horizontal line going through the y-intercept 0. So that's this line.
Necessary to say
What?
it's trapped y 0. Isn't that?
Yeah, that's kind of assumed, right? Because we're always trapping ourselves by the x-axis. So that is kind of assumed. Yeah, it might be a little unnecessary to say. But this is our thing now. And we're going to rotate this out and around the board. So it's going to go down, down, curve. Yeah, so that's what it looks like. You have to keep in mind that you're going to turn that thing into a 3-dimensional solid and set it down. It kind of looks like that, like a Christmas tree stand. Right? Not to scale, but that's what people put a Christmas tree stand looks like. It's a very small Christmas tree for such a large stand.
I was going to say, small.
It's deep. All right, so now we know what we're taking the volume of, and in fact, that was like a lot of information to think about something that's really quite simple, because our formula is from a to b of pi f of x squared. And so all we really need to know is we're going from 3 to 4, so that's our integral, right, from 3 to 4. Pi is a given, and our function is 2x squared. So it's 2x squared squared. Now this is normally what I see people forget, is that they see the 2x squared and then they forget to square it, and then they do the whole integral on the top. Remember, the formula is pi r squared. It's the formula for the area of a circle, pi r squared. So it's pi something squared. Make sure you put the square in. Okay, well, that's as far as we need to go together, because this is just pi 4x to the 4th dx. And what can you do with the 4 and the pi? Yeah, we'll just bring it outside. So it's 4 pi, 3 to the 4 of x to the 4th dx. I'd really like to impress upon you that for such a sophisticated thing, that we're calculating the area of a curvy mass. Look how easy that integral is. Like, it's very, very quite simple. Like, this is a big payoff, a huge payoff. That if you went back to the 1500s and you're like, find the volume of this thing, they'd have no idea how to do it. Yeah, now that reminds me of a story of Archimedes. Okay, do you remember the story of Archimedes where the king comes to him with his crown? It's a golden crown. Wow, that doesn't look like a crown. And it has jewels in it. Anyway, just pretend that it's a crown. Okay, that's a crown. And it sits on somebody's head. And they're happy about it because they're the king. So he had this crown theoretically made of gold, but the king thought that somebody had cheated him. And they had not just made it of pure gold, they had mixed in all sorts of base metals like, just iron. And he asked Archimedes, I want you to prove that this is real gold. And Archimedes was like, well, if I melt it, I can check the, the volume and see if it's real gold or if it's mixed with other things. And the king's like, no, please don't melt the crown. That kind of like negates the whole thing. Then I won't have the crown anymore. So he had to come up with the volume of the crown without harming it in any way. So do you know how he found the volume of the crown? Not math. You would think math, right? Because he found the volume of a circle, or the volume of a sphere. And we could do the volume of a crown now. You just have to come up with a sufficiently complicated function. And you can find the volume of this thing. So Archimedes had the brilliant moment of insight, so the story goes, he was in the bathtub, that he realized that if he had a bucket of water and the level was here, and then he dropped the crown inside the bucket of water, the water level would go up, and then he could just measure how much water went up, and now he'd gone to the crown. Believe it or not, that was like the first time somebody realized that like water displacement can calculate volume. I know, it seems really idiotic to us. So anyway, when he realized that, as the story goes, he was sitting in his bathtub, he got all excited that he realized how to find the volume of the king's crown. Then he jumped out of the tub naked, running down the streets shouting, Eureka, Eureka. Have you heard that phrase? Eureka? Eureka! So anyway, the whole story is, it's probably a false story, but the idea is that Archimedes jumped out of his tub butt naked and ran down the street shouting Eureka because he figured out how to find the volume of the crown. Had you heard this story before?
Yeah.
Maybe yes, maybe no. That's the story. All right.
And what was the screaming Eureka?
Eureka, I think it's, I found it. I think that's what Eureka means. I could be wrong. Okay, so the next one, do you think we can set this one up real quick? Now again, see, I gave you the Desmos graph. You'd have to find this Desmos graph on your own. So, yeah. So you're still just going to go from A to B. So what did it say? Find the volume of the solid formed by rotating the region enclosed by that, and that. Exactly, right? That, and that. So, but it works the same way. What does eta look like? It's exponential. Y equals 0 is the x-axis. X equals 0 is the y-axis. And x equals 0.5 is a point right here. So do you all see the solid that we're rotating? It's that guy. And that's what I drew for you on this graph. It's that piece right there. And so it's going to rotate around and around the x-axis. And so we're going from 0 to 0.5. And the function is just e to the 2x plus 4. So we write down our function, or our integral, from 0 to 0.5 and 5. This one's actually going to be a little tricky. E to the 2x plus 4 squared. So remember the other integral we did when you were squaring a square root, and you're like, how convenient, it cancels the square root. Is this square convenient? No, because what do you have to do to this? Yeah, you get to foil it. You get to foil that out so that you'll have a trinomial. Substitution. That would be nice, wouldn't it? I don't know. You can try use substitution. I've never thought to do use substitution. I always just foil it out. That's a really fun idea, Josh. You can try use substitution and see how it works. But I would just foil, so what? E to the 4x plus 4 e to the 2x plus 4 e to the 2x plus 16. So then you'd end up with, I'm doing too much here, and I know class is over 5. So that'd be e to the 4x plus 8, e to the 2x plus 16, and then that's your integral. Okay, well, we accomplished a lot today, folks. We finished the previous section. We talked about area between two curves. We talked about the volume of a solid of revolution. And so we have all of the next class period to finish. And we have a couple more ideas. The average value. Yeah, in fact, we're doing really well on time. We're actually going to finish early next time. I'm going to chuck the woodchuck. You know, the funny thing is, a woodchuck is a small animal. It doesn't chuck wood at all. That's the irony. But listen to the rhyme. How many chucks could a woodchuck chuck if a woodchuck could chuck wood. So they're acknowledging that the woodchuck doesn't even chuck wood. It's such a ridiculous rhyme. That's like asking how fast could pigs fly?
Well, they don't fly.
You needed a second?
Oh, yeah, sorry. Josh, here's your signatures. I wrote down that you've been absent from every class. Yeah, let me give you your test. Thanks, Colleen, for reminding me. I already erased my reminder. Rosa. Joshua. Taking the haircut, Josh, by the way. Sarah. Holly. Fatima. Molly. Monica. And then. Hey, Juan, if you hang out, I'll give you your test.